Okay, hello and welcome to our third session. So on this third session, we are going to have now our chapter 1, simple stress. So the simple stress we have to learn. So it is expected that you will be able to distinguish different types of internal forces, describe material behavior under different types of stresses, construct comprehensive free body diagram. As usual, we have been doing this since the mechanics, relate to different formulas, variables, and units involved in the simple stress. And of course, we should have to learn how to interpret and discuss results of analysis of internal forces. Okay, so this topic is called out from this reference, Vital A. Singer F. 1980 Strength of Materials, 3rd edition. So it came from the principle that the sigma or the simple stress is equal to force all over area. So force all over area. So simple stress can be classified into normal stress, shear stress, bearing stress. So we have actually had a discussion on this type of stresses. So the formula is similar, only that the force varies accordingly. Like the normal stress is a force oriented parallel to the member, or what we call the normal axis parallel to the member. And then for the shear stress, it is caused by a force that is cutting the cross section of the member. And for the bearing stress, these are stresses that are caused by contact between two surfaces. As for the system of units, we have SI, English, and US customary. For megapascal, it could be in terms of Newton per millimeter squared or meganewton per square meter. So in English system, it could be in terms of pounds per square foot or PSF, or could be in terms of pounds per square inches or PSI. For US customary, we have KSI or kips per square inches. So the basic principle here is just that the force is just distributed on the cross-sectional area involved here. So let us start with the first one. We have here the normal stress. Okay, so the normal stress is also called as an axial stress. It could either be tensile stress or compressive stress. We had actually learned this one when we have the bar in tension. The force is directed away from the member, and when we have bar in compression, the force is directed towards the member. So just the same, this is sigma is equal to P over A, the normal force all over the cross-sectional area. So in order to have a uniform distribution of force on the cross-sectional area, we must have to satisfy three. Number one, the member should be homogeneous. When we say homogeneous, when we use, for example, when we use a steel material, it is a steel material all over the entire length. So there's no such thing as the change in material. Secondly, the material should have a uniform cross-section all over the entire length. So when we have a circular section, it should be a circular section all throughout the entire length. So there's no change in cross-section all over the entire length. And then for the third one, the force must be axial. So again, the force must be oriented along the axis of the normal axis. Okay, so For the sign convention, remember that tension is stretching, so we denote that as a positive, and the compression is shortening the member, so we denote that by negative sign. Okay, so that's the principle. This is simple. Just stick the formula sigma is equal to P over A. So just remember that the sigma in every structural member, there are limit. So this limit is what we call the allowable. So if we exceed the allowable, of course, expect that the material will begin to fail or will begin to deform. Okay, so let us proceed now to illustrative examples. So these illustrative examples is the same. It is retrieved from this reference. Okay, so we have here a hollow steel tube. So when we say a hollow steel tube, the center core is open. So this is open space. This is not solid. Okay, so this problem, we have to apply again of course, this formula sigma is equal to P all over A. Okay, so the given here is that this tube will carry this axial load. Okay, so we can see that P here is axial or parallel to the member. So if the member is vertical, P is also vertical here. So obviously this will shorten the hollow steel tube. So it will act as a column. Okay. So when we cross multiply this one, we will come up with this expression. So for the given, we have a limit or the allowable 120 megapascal and the actual load 400. So our task is just to determine the diameter, outside diameter, and 100 here is fixed according to the problem. So it is just a matter of determining the outer diameter so that this shaded portion here is sufficient enough to carry this 400 kilonewton. Okay, so as simple as that. So we'll now proceed to the computation of the area. So this area, it is just a matter of having a larger circle less a smaller circle. So when we remove this portion, it will have an area like this. So it is the area of the larger circle less the area of the smaller one. Okay, that is why we have this expression. And then we factor out 1/4 pi as a common factor of this expression. And then 100 squared is actually 10,000. So further, we use that formula now and come up with this. We substitute P. Remember that before we substitute to this formula, let us be consistent in our units. So this is expressed in Newton. So we have 400,000 is equal to the area, this one. This 120 here is the sigma, and this one is the area. This one is the area. And then upon manipulation of the equations, we come up with this requirement. So this is diameter, or we can round this up to 120 millimeters. So do not ever round that down, because the implication is that if we round that down, this is the minimum, and if we have a value less than the minimum diameter or cross section, the implication is a failure. So So this is problem number 1 all about. So please stand by for another video for another example. So thank you. I hope this helps.